Okay, let's unpack this. We're diving headfirst into the incredibly exciting and honestly maybe a little bit scary world of agentic AI. Forget AI models that just respond to prompts you give them. We're talking about autonomous agents here, systems that can actually think and act on their own. Plan complex tasks, delegate work to other agents, and collaborate across different systems, different teams, even different organizations. Imagine software that doesn't just wait for instructions, but actively seeks out other software agents to get its job done. But here's the challenge that immediately jumps out. As these agents start talking to each other, especially across boundaries where they might not know or, inherently trust the agent they're interacting with, how do you ensure that communication is secure? What stops a rogue agent from pretending to be another to steal data or subtly tampering with crucial instructions for a task? The potential security nightmares are pretty significant if we don't get this right from the start.
And that's exactly why secure protocols aren't just a nice to have. They're absolutely foundational for building, reliable agent ecosystems. You need a way for agents to verify who they're talking to, authenticate their identity, securely exchange sensitive tasks and the resulting data, and, critically, maintain a clear, auditable record of what happened.
Exactly. And that's where something like Google's agent-to-agent or A2A protocol comes into play. It's designed to be that secure plumbing, right? That trusted foundation for autonomous agents to discover and interact with each other in a structured way. So our mission today, digging into the material you shared, is to take a deep dive into A2A itself and also the specific, sometimes unique security challenges it faces and how experts are proposing we tackle those risks, particularly by using a threat modeling framework designed specifically for AI security called MAESTRO. Think of this as getting a critical head start on understanding how we build trust and security into these next-generation AI systems as they start showing up everywhere. So to kick things off, when we talk about agentic AI, what makes it fundamentally different from the AI we've seen before, and why does secure communication become such a much bigger deal now?
Well, what's fascinating here is seeing the evolution in action. We've certainly had powerful AI models, but they were primarily reactive. You send a query, they give you an answer. Autonomous agents are different. They have goals, they can make decisions about how to achieve those goals, they can use external tools, and critically, they can collaborate and delegate tasks to other agents. They don't just wait. They can initiate interactions based on their internal state and objectives. It's a real shift.
Right, proactive instead of just reactive.
Exactly. And if we connect this to the bigger picture, as these agents start interacting across organizational walls, different networks, or simply where they haven't met before and don't have built-in trust, secure, standardized communication becomes paramount. If their conversations are vulnerable, the risks are immediate. One agent could impersonate another. Sensitive data could be exfiltrated during an exchange. The instructions within a task could be subtly tampered with, leading to incorrect or, malicious actions, or an agent might gain unauthorized privileges by exploiting a weak link. This is why protocols for identity, authentication, how tasks are structured and exchanged, and ensuring you can audit the interaction history are really non-negotiable.
Okay, this is where A2A looks promising then. How does Google's A2A protocol aim to provide that structured, secure communication framework for agents?
So A2A is presented as a significant step towards enabling structured, secure, and interoperable communication specifically between agents. It puts a strong focus on composability, meaning you can build complex agent systems by combining simpler, specialized agents, and crucially, on building trust into those interactions. At its core, A2A allows agents to discover each other, authenticate their identities, and exchange units of work or tasks in a defined, standardized way. A key design choice is that it builds heavily on widely adopted web standards, things developers are already familiar with, like HTTP for transport, JSON RPC for defining the commands, and server-sent events, SSE, for getting streaming updates. This foundation, it helps accelerate adoption.
Right, less friction.
Exactly. The core principles really define it. It's agentic first, meaning it's designed for independent agents explicitly communicating. It's standards compliant, leveraging that existing web tech. And importantly, it aims to be secure by default, with security considerations integrated into the protocol design itself.
Okay, let's unpack this communication flow then.
Yeah.
If one agent, let's call it the client agent, needs something done by another agent, the remote agent, how does that interaction actually start using A2A? It begins with discovery, right? How does one agent find another in this system?
That's exactly right. The client agent first needs to find out who the remote agent is, what specific things it can do, and importantly, how to securely initiate communication with it. The central innovation here, based on the source, is the agent card.
The agent card, okay.
Yeah, think of the agent card as a standardized, machine-readable business card for an agent. It's just a JSON file, but it lives at a predictable standard location relative to the agent's web presence. .wellknownagent.json.
The well-known location, like for other web standards.
Precisely.
Yeah.
This standard location is brilliant because it makes discovery straightforward across the ecosystem. An agent knows exactly where to look for another agent's public information. This agent card contains essential details: the agent's unique ID, the specific endpoint URL where you send A2A requests, A2A endpoint URL, a catalog listing its available functions or capabilities,
Okay.
details on the authentication methods it requires using standard open API security schemes, and descriptions of what the agent can do.
Got it. So the client agent finds the agent card, gets the address and necessary info. What happens next in this flow, moving from discovery to initiation and processing?
Right. So after successfully discovering the agent card, the client agent moves to initiate the interaction. It authenticates using one of the methods specified in the agent card, maybe with a token or certificate. Then it sends a JSON RPC request to the A2 endpoint URL discovered earlier. This communication happens securely over HTTPS naturally. The protocol defines methods for sending tasks. You'll typically use tasks.send for requests that might be synchronous or where you don't need constant updates, and tasks.send_subscribe if you need streaming updates on a long-running task via server-sent events, SSE.
Okay, so synchronous versus streaming.
Exactly. And the processing differs based on which method you use. For tasks.send, the server agent processes a task and sends the final result, the completed task object, back in the single HTTP response. Simple enough. For tasks.send_subscribe, it's different. The server establishes a persistent HTTPS connection and streams updates about the task's progress or any results it generates as they happen using those SSE messages. More like a continuous feed.
What if the remote agent starts working, but hits a point where it needs clarification or maybe more data from the client agent to proceed? How does that work?
Yeah, good question. The protocol handles that with an input required state. The server agent signals this need either in the response to a tasks.send or via an SSE event in a streaming interaction. The client agent then provides the necessary subsequent input by sending another request or message linked to the same task ID.
So it keeps the context.
Exactly. It allows for a conversational turn-by-turn interaction within a single task. The process continues until the task reaches a completion state it's finished, failed, or canceled. The source also mentions an optional push notifications capability where the server can send asynchronous updates to a webhook URL the client agent provides.
Oh, that's useful.
Yeah, it's useful if the client doesn't want to maintain a persistent connection,
Okay, so just to quickly summarize the core pieces we've discussed. We have the client agent and the remote agent communicating. The agent card is that machine-readable identifier and guide for discovery. The fundamental unit of work is a task, which progresses through different lifecycle states. They exchange messages, which are like dialogue turns containing structured parts, that's the actual content, like text, files, or structured data. And agents can produce artifacts, which are outputs resulting from the task execution, also containing parts. Did you get that right?
That's a solid overview of the key concepts in A2A. You nailed it.
Great. Before we really dig into the specific security risks A2A systems face, it might be helpful to look back for context. How did systems handle security, especially when dealing with distributed services or maybe early forms of agent-like interactions, before modern protocols like A2A came along?
Right, looking back is useful. Historically, various approaches were used, each with its own strengths and, weaknesses when thinking about autonomous agents. Traditional PKI, public key infrastructure, using digital certificates and SSL/TLS was great for securing the communication channel itself. But managing certificates for large dynamic populations of agents became incredibly complex operationally. Just a nightmare. SOP with WS security provided robust message-level security, ensuring the integrity and confidentiality of individual messages, but it was quite verbose and heavyweight. Probably more suited to tightly coupled enterprise environments.
Yeah, SOP could be pretty heavy.
Definitely. Then OAuth 2.0 and JWTs, JSON Web Tokens, became standard for identity and authorization, but they were primarily designed around user-centric flows. Adapting their interactive nature to autonomous machine-only environments securely was challenging.
Right, forcing a square peg into a round hole sometimes.
Kind of, yeah. And zero trust principles, like those embodied in Google's BeyondCorp, started pushing towards continuous validation regardless of network location, which is conceptually aligned with securing decentralized agents, but wasn't a full protocol solution itself.
And what were the key problems or limitations that really became apparent when trying to apply these older methods specifically to autonomous agents interacting autonomously? What were the sticking points?
The sources highlight several critical limitations. A big one was manual credential management. The sheer overhead of provisioning, rotating, and revoking static secrets or certificates for potentially thousands or millions of agents was immense, just not scalable. Adapting user-centric models like OAuth 2.0's browser-based flows to machines often forced awkward workarounds, frequently resulting in the use of less secure static credentials or service accounts that pose their own significant risks.
Right, those long-lived keys are always a worry.
Always. There was also a significant lack of uniform standards, leading to fragmented custom security implementations across different systems. This made interoperability and consistent security practices really difficult. And simply put, as the number of agents and their interactions grew, the operational complexity and the attack surface scaled dramatically, making the older, less automated approaches unsustainable. This really underscored the need for security models and protocols designed specifically for autonomous agent interactions.
Right, something built for this new world.
Yeah.
Which brings us to threat modeling, thinking about the specific risks, securing systems with autonomous decision-making, tool-using agents collaborating. That sounds complex. Potentially introducing new kinds of vulnerabilities we haven't seen as much before. Traditional security models might not capture all the nuances, right? So how do experts approach identifying the risks in these A2A-based systems? What's the methodology?
That's a really important question. How do we even think about agent security systematically? Traditional threat modeling frameworks like STRIDE or OWASP are valuable, absolutely, but they don't always fully account for the unique characteristics of AI models and multi-agent systems. That's why the MAESTRO framework was developed. It's a 7-layer threat modeling framework designed specifically for agentic AI systems.
MAESTRO, okay.
Yeah. It extends existing frameworks, but adds layers and considerations unique to AI capabilities and the way multiple autonomous agents interact. It really emphasizes that security needs to be built in and considered at every layer of the system, from the underlying AI model all the way up to the entire ecosystem of interacting agents.
Can you give us just a quick sense of what some of these MAESTRO layers cover, just a flavor?
Certainly. While there are 7 layers in total, some key ones give you a feel for it. There's the foundation models layer itself, focusing on the security of the core AI. Makes sense. Data operations looks at the risks related to the data agent's user process. The agent frameworks layer is crucial for us today. That's where protocols like A2A live, and its vulnerabilities would be analyzed.
Okay.
Then you have deployment and infrastructure, security and compliance layers, and finally the agent ecosystem layer, which specifically looks at threats that emerge when multiple potentially untrusted agents interact and collaborate.
Okay, this is where it gets really interesting for A2A specifically. Using this MAESTRO lens, what were some of the specific, perhaps unique security threats identified for systems built using the A2A protocol that stood out from the source material? Let's unpack those.
Right. Applying MAESTRO surfaced several specific threats unique or particularly relevant to A2A-based systems. One clear one is agent card spoofing. Because the agent card is just a file at a standard location, an attacker could potentially host a fake agent card, maybe on a domain with a similar name or by compromising a legitimate server.
Okay, like typo squatting but for agents.
Exactly. A client agent performing discovery might accidentally fetch and trust this fake card, sending sensitive tasks or data directly to the attacker's rogue server instead of the legitimate one. This sits at the agent frameworks and deployment layers in MAESTRO.
Yikes. Okay, what else?
Then there's A2A task replay. If an attacker intercepts a valid request to send a task, say using tasks.send, they could potentially just send that identical request again to the legitimate server. Without proper protection against replay attacks, the server might execute the same task multiple times, leading to duplicate actions, unintended side effects, or even financial costs depending on the task. This is primarily an agent frameworks layer issue, also touching on data operations.
Right, basic replay attack, but in this new context.
Exactly. Now, what's truly fascinating here, and quite unique to AI agents that might process metadata using their underlying models, is the poisoned agent card.
Poisoned agent card. That sounds nasty.
It really is. This exploits the fact that agents often use their underlying AI model to understand the content of information, even within structured data, like an agent card. An attacker could inject malicious instructions, basically, a form of prompt injection into fields within a seemingly legitimate agent card, like a skill description or maybe an example usage.
So hiding instructions inside the description.
Precisely. When another agent discovers this card and processes that content to understand the remote agent's capabilities, maybe as part of its planning or execution flow, its underlying model might interpret and execute those hidden instructions. It exploits the trust placed in the agent card's content and the agent's automated processing. The impact could be severe, hijacking the agent's intended goals, causing it to reveal sensitive internal data, or tricking it into performing unauthorized actions.
Wow, that's subtle.
It is, and this threat spans multiple MAESTRO layers. Foundation model, where the injection is processed, data operations, as the card content is processed, and the agent framework. It really highlights how AI model vulnerabilities intersect with protocol design.
Okay. What other threats came up?
We also see traditional authentication and identity threats, but applied to the agent context. A2A relies on standard web authentication methods like JWT tokens. So risks include attackers forging or stealing tokens, servers failing to properly validate tokens like skipping signature checks, which is a surprisingly common mistake.
Yeah, I've seen that.
Token replay, or sensitive tokens being stored or transmitted insecurely. This impacts multiple layers: agent frameworks, deployment, security and compliance, and the overall agent ecosystem. A JWT is basically a standardized way to send claims like I am agent X between parties securely. Validation is absolutely key to trust those claims.
Makes sense.
And linked to that is cross-agent task escalation in the agent ecosystem layer, impacting the agent framework. A malicious agent could enumerate available agent cards, identify potential targets, and then try to use forged or stolen credentials to submit tasks that granted unauthorized access or higher privileges to sensitive data or actions it shouldn't have.
Trying to level up its permissions, maybe.
Exactly. Other threats mentioned in the source include things like artifact tampering, modifying the outputs an agent produces, and insider threat issues where an agent with authorized access might misuse it.
Wow, okay, that does sound like a lot to worry about.
Yeah.
So what does this all mean for someone actually trying to build or deploy systems using A2A securely? What practical steps can be taken based on what the source material outlines to mitigate these specific risks we just talked about?
Right, that's the critical question. How do we translate these identified threats into concrete security practices? The good news is the source provides a pretty comprehensive list of mitigation strategies, often directly countering the specific threats we just discussed.
Okay, let's hear them.
So, to address agent card spoofing, the recommendations are clear. Use digital signatures on agent cards, ideally signed by a trusted certificate authority. This verifies the card's authenticity. It came from who it says it came from. You also need secure agent card resolution. That means fetching the card strictly over HTTPS with proper certificate validation and maybe even certificate pinning. This ensures you're talking to the correct server when you get the card.
Right, secure the lookup process.
Exactly. Using a trusted registry for agents could also help validate cards. And crucially, sanitizing the content within the agent card before an agent's model processes it helps protect against that really sneaky poisoned agent card threat.
Sanitize everything. Got it. What about task replay?
For A2A task replay, standard techniques apply, adapted for the protocol. Include a unique nonce in requests that's a one-time code that makes each request unique, so replaying the old one won't work. Use timestamp verification to ensure requests are recent. Employ message authentication codes, MACs, to ensure the message hasn't been tampered with in transit. Where possible, design tasks to be idempotent, meaning performing the action multiple times has the same effect as doing it once. That limits the damage from replays. And implement proper session management if the interaction involves a session state.
Okay, and for the poisoned agent card and general schema issues?
Mitigating the poisoned agent card threat and general message schema violations heavily relies on robust input validation and sanitization. Enforce strict schema validation against the A2A protocol definition. Make sure messages are correctly formatted. But even more importantly, sanitize all input received from clients. This includes the agent card content itself and the content within message parts. Sanitization means actively cleaning the input to remove or neutralize anything that could be interpreted as a malicious instruction or code snippet.
So don't just trust descriptions or examples.
Absolutely not. Use allow lists or escaping for special characters. Content security policies, CSP, might also be relevant if agents use components that process content in a web-like environment. It's about defensive coding.
Makes sense. How about the authentication and identity threats, JWTs and such?
Right. For authentication and identity threats, strong JWT validation is paramount. You must check the signature, audience, and issuer claims of tokens. No shortcuts. Secure token storage and transmission are critical. Token rotation limits the window if a token is compromised. And using MTLS, mutual TLS, for API access adds an extra layer of security because both the client agent and the server agent verify each other's identity using certificates, not just the client verifying the server.
Mutual authentication. Good point.
Yeah, it significantly raises the bar.
And preventing that cross-agent task escalation.
Preventing cross-agent task escalation requires rigorous authentication and authorization checks on every single task request. Validate the incoming credentials every time. Implement detailed audit logging of authorization decisions so you know who tried to do what. Strictly adhere to the principle of least privilege agents only get the permissions they absolutely need, nothing more. And ensure secure discovery mechanisms for agent cards so attackers can't easily map out targets. The source also emphasizes general security best practices applicable to building A2A systems, continuously scanning software supply chain dependencies for vulnerabilities.
Oh yeah, gotta watch those libraries.
Definitely. Having clear incident response plans, evaluating the security posture of any open source libraries used, preferring declarative configurations for predictability, integrating security testing unit, integration, even adversarial tests trying to break the AI logic into the development pipeline, and thoroughly documenting agent capabilities and trust boundaries within the agent cards for clarity and security auditing.
Okay, that's a solid list. The paper looks at a couple of specific scenarios too, right? To illustrate how these threats and mitigations actually play out in practice.
Yes, exactly. They use simplified case studies, like agents collaborating on a complex document processing workflow or agents analyzing distributed data across different sources. These examples help illustrate how risks like prompt injection, not just via a poisoned agent card, but even via malicious content in message parts or data leakage through improperly handled artifacts, or that agent card spoofing we talked about, can manifest in real-world scenarios.
So making it more concrete.
Yeah. What they really show is how these risks can span multiple layers of the MAESTRO framework and cross traditional security boundaries, demonstrating why you really need a holistic security approach, not just point solutions.
It makes sense that A2A helps agents talk to each other, agent to agent, that sort of horizontal collaboration. But agents often need to reach outside to interact with external tools, APIs, or databases, right? Is there another protocol that fits in here?
Absolutely, and the source points directly to the Model Context Protocol, or MCP, as a complementary framework.
Like a CP, yeah.
Yeah. While A2A is designed for that agent-to-agent communication, think of it as peer-to-peer conversation between autonomous entities. MCP standardizes how AI models or agents connect with external tools and data sources. That's more of a vertical integration, reaching out from the agent to the external world.
Okay, so A2A for agent-to-agent, MCP for agent-to-tool data. How would they work together in a sophisticated agentic system then?
The source gives a really clear example. Imagine a main agent receives a complex task, maybe coming in via an A2A request from another system. To fulfill it, this main agent might need to delegate parts of the work to specialized agents. It would use A2A's discovery mechanism to find these specialized agents and then assign subtasks to them, communicating via A2A.
Standard delegation.
Right. Now, one of those specialized agents might need to use an external tool, say a weather API or a specific database. That specialized agent would then use the MCP to connect to that specific tool or database, interact with it, get the necessary data or perform the action, and then pass the results back up the chain, communicating with the main agent again via A2A.
I see. So it's a multi-protocol flow.
Exactly. This multi-protocol architecture allows for incredible modularity and flexibility. You can build really complex workflows by chaining agents and tools together. But, and this is crucial, it introduces critical security considerations at the integration boundaries. A vulnerability at the A2A layer could potentially be exploited to compromise an agent that then uses a vulnerable MCP connection to exfiltrate data from an external system or vice versa.
So the seams are potential weak points.
Precisely. Robust security needs to cover not just each protocol in isolation, but meticulously secure how they connect and interact. You have to look at the whole picture.
The paper seems to go into quite a bit of detail on the server side. What's needed to actually implement a secure A2A server? What are some of the absolute must-dos the source outlines for developers building these servers? The nitty-gritty.
Yeah, implementing a secure A2A server requires careful attention to several key areas, really building security controls right into the server's logic. The source highlights quite a few must-dos. First, securing the agent card itself is fundamental. It needs to be hosted securely with access controls and, rate limiting. You should only include necessary information. clearly specify required authentication methods, and validate its content regularly, especially against the possibility of it being poisoned with malicious instruction.
Okay, protect the business card.
Exactly. Then, authentication and authorization are non-negotiable for every single interaction. The server needs its own strong identity, typically using digital certificates and TLS, so clients know they're talking to the right agent. You must declare supported auth protocols in the agent card and rigorously authenticate every single incoming request. No exceptions. Beyond authentication, who you are, you need strong authorization, what you are allowed to do. Protect sensitive actions or data by carefully managing authorization for the skills the agent offers and any tools it might control, maybe using concepts like scopes or granular permissions. If using API keys or JWTs, follow all best practices, rotation, secure storage, and critically robust validation of every part of the token. Check everything.
No skipping checks.
Never skip checks. Secure communication means enforcing HTTPS with a strong, modern TLS configuration like TLS 1.3. Encrypt data not just as it travels, but also at rest if the server stores any sensitive task data persistently. Validate certificate chains correctly and consider certificate pinning for critical connections to prevent man-in-the-middle attacks.
Standard web security, but applied rigorously.
Exactly. Input validation and request processing is absolutely vital for preventing many common web vulnerabilities and those agent-specific injection attacks we talked about. Validate all incoming messages against the A2A protocol schema. Implement robust sanitization on all content received, especially anything destined to be processed by an underlying AI model. This is your primary defense against poison agent cards and prompt injections via message parts. Validate URIs to prevent server-side request forgery, SSRF, where an attacker tricks your server into calling unintended internal or external URLs, and handle file parts securely, scan for malware, validate file types and sizes, store them securely, definitely outside the web root.
Lots of validation points there.
There are. Server implementation best practices also include comprehensive error handling that avoids leaking sensitive details, maintaining detailed security logs for authentication, authorization, task events, and security incidents, and protecting those logs. Implement rate limiting and DOS protection on endpoints. Follow secure coding guidelines and integrate security testing unit tests, integration tests, and even adversarial tests trying to confuse or compromise the AI into your CI/CD pipeline.
Testing for AI weaknesses, too. Interesting.
Yeah, it's becoming necessary. For protocol specifics, if you support streaming with SSE, ensure authentication applies to those long-lived connections, manage session state securely, and protect against resource exhaustion. If you use push notifications via webhooks, rigorously validate webhook URLs and verify signatures on webhook payloads. Connection management quotas, limits, timeouts is essential to prevent abuse of persistent connections.
Manage those connections carefully.
You have to. Finally, server hardening of the deployment environment is non-negotiable. Think network segmentation, using web application firewalls, WAFs, applying regular security updates, comprehensive monitoring for suspicious activity, and having incident response plans ready before something happens. Regular security assessments and penetration tests are also key.
Okay, that's a thorough checklist for server implementers. So where does this deep dive into the sources leave us looking ahead? What's next on the horizon for securing this burgeoning world of agent collaboration?
Well, based on the source material, future directions seem to involve continued effort towards more protocol standardization, with security, hopefully even more deeply prioritized right from the outset. There's a recognized need to adapt zero trust principles more concretely for agent-to-agent interactions, never trust, always verify, applied to autonomous agents.
Makes sense for agents that might appear anywhere.
Exactly. Developing standardized ways to express and enforce complex authorization policies between autonomous agents operating across different trust domains is a big challenge that needs tackling. Robust agent identity verification and perhaps even reputation management systems will likely become increasingly important. How do you know an agent is trustworthy over time?
Yeah, reputation is interesting.
Secure coordination and orchestration across trust boundaries and complex multi-agent systems, addressing the specific security implications of integrating large language models deeply into these workflows, and collectively developing shared guidelines and comprehensive threat models like MAESTRO. These are all seen as crucial steps for building genuinely trustworthy and reliable agent ecosystems.
So we've gone pretty deep into Google's A2A protocol. We've seen how it provides a structured way for agents to discover and talk to each other, which is cool. But we've also uncovered the critical and sometimes really unique security challenges involved. Everything from a seemingly simple agent card being spoofed or even poisoned with hidden instructions to malicious agents trying to replay tasks or escalate their privileges across the ecosystem.
And we've seen how structured approaches like the MAESTRO framework are pretty essential for identifying these specific AI agent-related risks, which then leads us to concrete mitigation strategies. Whether it's demanding digital signatures on those agent cards, implementing robust input sanitization for absolutely everything in agent processes, or applying strong authentication and authorization at every single interaction point, securing agent communication isn't just about encrypting the channel anymore. It's fundamentally about building trust at multiple layers, from verifying the agent's identity and capabilities to ensuring the integrity of the data it processes and the tools it interacts with via complementary protocols like MCP.
It's definitely clear that as agentic AI systems become more common, more complex, and more autonomous, building trust and security in from the ground up is absolutely non-negotiable. It's not an afterthought. It required careful protocol design, rigorous implementation, continuous vigilance, and understanding frameworks like A2A and MAESTRO to identify and address risks proactively. The sources you shared provide a fantastic foundation for getting a handle on these critical concepts.
Indeed. It's a fast-moving space, but the foundations are being laid now.
And thinking about the future, maybe something for you, the listener, to mull over. Consider the idea of agent reputation. As these autonomous systems evolve and start interacting more freely, maybe across potentially open networks, how might we build verifiable trust signals or reputation mechanisms between agents that need to collaborate without prior knowledge or centralized control? How does an agent earn trust? Something to think about as you start seeing agentic AI applications emerge and interact around you.